Welcome and thank you for joining us for this episode in the Fearless Minds research series, Nanodesign from Cancer Diagnostics to Nanoplastics Pollution. I'm Professor Claire Lenihan, Dean of Research in the College of Science and Engineering here at Flinders University. And it's my pleasure to welcome you to today's discussion as we explore nanodesign and its application across the environment, energy, production and medicine. To begin with, I'd like to acknowledge that we're hosting this discussion on the traditional lands of the Kaurna people and that we pay our respect to their elders past, present and emerging. We also acknowledge and convey our deep appreciation to the elders of all nation upon which Flinders operates. This event is delivered as part of our Fearless Minds series. Throughout the series, you will meet with some of Flinders University's most engaging early to mid-career researchers as they bring you their latest research from a diverse range of fields. Today, we're fortunate to be hearing from Associate Professor Melanie Macgregor, a Matthew Flinders Fellow in Chemistry here at Flinders in the College of Science and Engineering. Melanie is also an ARC Future Fellow in Materials Science, and her research group explores the effects of surface chemistry and nanoscale topography on the interaction with biomaterials and their environment. Melanie's research has been recognised through several awards, including the 2018 South Australian Young Tall Poppy Science Award. In 2019, she was also invited to participate in the Superstar of STEM program hosted by Science Technology Australia, which aims to promote gender equity and diversity in STEM careers. Melanie, thank you for joining us today.
Thank you for having me.
Welcome. To get started, I'd like to ask you, for the benefit of our viewers, from a non-scientific background, how would you describe your research field and what you do?
So I like to call it nanodesign. A bit like, architects are making brand new buildings these days with plenty of materials from glass, wood and metals and different shapes depending on what the building needs to do. I do a bit the same thing, but at a very small scale, the nanoscale. So just to put it into context, nanoscale is if you take a hair, one of your hair, and you cut it in 100,000 slides, that's about how thin and small the feature that I'm making are. So by doing that, I'm able to control how materials interact with their environments. So whether we want things in their environment to stick to them or to be repelled by the materials, and we can apply these principles to a wide variety of fields from medicines, energy, environments, lots of different things.
And I know that you're actually doing that in applying them to a number of different areas. So can you tell us a bit more about how nanodesign and you're working with it and to assist in results around cancer diagnostics?
Sure. So that was a project that was highly collaborative. We worked with clinicians, we worked with engineers, we worked with biologists, and my job in this project was to design the surface. So at the nanoscale, I made the surface so that it could absorb antibodies, which are like little hook that will specifically attach a kind of cell, the one that you're after. And in this case, the environment around my surface was urine. So the patient will give a urine sample, will run it over the surface, and the surface will specifically capture cancer cells if they're present in the urine sample. So this is a way that we're hoping would be able to help diagnose cancer in a non-invasive way, which is better than what we have at the moment, where people need to have something called a cystoscope, which is about that big, a wand with a camera at the end that you need to put up into the people's bladder duct to go and have a look around. So clearly giving a sample of your urine is a bit less invasive and a bit nicer for patients.
That certainly sounds much more pleasant than the alternative. I think that sounds wonderful. You're also working in nanoplastics, so can you share a bit about the work you've been doing there?
Sure. So this one is a new project. You're probably aware that plastic pollution is a big issue. About 80% of it end up in the environment when we dispose of them. And these plastic bags, anything, will break down. They'll break down in microparticles, which we know a fair bit about. We already know that we find them in animals and plants. But when these microplastic break down even further, at the nanoscale, we know a lot less about them because the instruments to detect them are not quite available, it's difficult. And so in my research, I'm trying to develop new kind of filters that will modify chemically so that they can capture nanoplastic from the water of lakes, the sea, your tap water, any kind of samples to help then detect these nanoplastics, see where they are, and then further down the track, maybe study a bit more about their toxicity as well. Because at that scale, there is a risk that the nanoplastic can actually cross the cell membrane. So it's not just you're eating them, they are so small that they can penetrate your cells where, you know, your DNA and all the other organelles are. So it's a new kind of pollutants that the biologists are very interested into looking at as well.
So it's very much an emerging pollutant. It's very clear as you're talking that there's lots of applications in many different industries, from the medical industry to the environment. You're also doing some work in the energy industry. So can you tell us about the project you're working on with nanotechnology and green fuels?
Sure. So in this project, it's a little bit different. We're modifying the surface to make it so that it can trap air. What we're trying to do is help our collaborator in Switzerland who wants to convert nitrogen from the air into ammonia. Ammonia we already use a lot as fertilizer to help keep up the production of food for humans and animals. But apparently it can also be a very good green fuel that is carbon-free, that is more high-density energy than liquid hydrogen, easier to carry and transport. And so there's a lot of interest into making ammonia. And one way of making it is from the D-nitrogen that is everywhere around us in the air. But it's difficult to do, and to do that we need some new catalysts that can trap air where the nitrogen is to help transform it into the ammonia itself. The process that's using that at the moment is very, very polluting. It's responsible for more than 1% of the world production of CO2, so we need to move on and do something a bit better.
Oh, wow, that's wonderful. If we can achieve that goal, that would be fantastic for our environment. What drives you to keep searching for answers in the field and these diverse projects, and what inspires you?
Well, I think that as a scientist, like many young kids, I probably decided to study science to change the world, make it better. And I always loved chemistry, but chemistry has had a little bit of a bad name for many years, responsible for some pollution. And so what's keeping me motivated is that now we can use chemistry to actually clean up and do things in a more sustainable way. So it's really a very noble goal, and it's selfless. You wake up in the morning, you're trying to do something good, not just for yourself, but also for the planet. And yeah, you can always reflect back on that when it's a bit hard.
That's great. That's a great goal to have. So just you tell us a bit about your advice. So you completed your PhD in 2013. What would your advice be for anyone thinking of a research career in this field?
So I guess one of the things I realized in my project is that I studied chemical engineering to start with, but I've really worked in very multidisciplinary projects. So all kind of disciplines. So from biology, physics, engineering, even programming, things like that. Everything is entangled. So one advice would be to not drop any kind of science too early on, because you will need it. Or you'll have to relearn. That's possible too. So that's one thing. I found it very useful to touch a bit of all the STEM disciplines. The other one is really just to listen to what is your passion, what you like, look at what you're doing. When I was little, I was making mixture and potions in the bath and in the sandcastle, so clearly that was chemistry. So I just followed that path. It was quite easy. So do something that you really like, naturally speaking, and I think it will be easier to wake up to a job that you like every day. And maybe just one more thing is maybe for the young girls out there, there's many of us in the STEM field, so don't be scared. If that's your thing, come and join us. We'll help if you need some help. We support each other, and so it's a really good field to work in.
As a chemist myself, I can really relate to your comment about the potions in the bath and making mixtures. What a wonderful and insightful discussion we've had today. Thank you so much, Melanie, for sharing your time and your knowledge and your experience with us.
You're welcome. It was a pleasure. Thank you.
Great. Remember, you can watch any of our Fearless Minds episodes on the Flinders YouTube channel. We hope you keep an eye out for the next one. Thank you once again, and bye for now.